Linear equations. Any equation must have at least one variable. Linear equations have either one or two variables and may also have a constant. The variables in a linear equation are not raised to any power beyond 1, so you won't see any exponents, and they are not squared or cubed or etc. You won't see an exponent of 2, an exponent of 3, etc. The standard form of a linear equation is ax plus by equals c, where x and y are the variables, a and b are coefficients, and c is a constant. Now the coefficients and the constant a, b, and c are integers, and then the coefficient in front of x, a, is greater than or equal to 0. There are an infinite number of solutions to a linear equation. In general, each solution is an ordered pair of numbers representing the values for the variables that make the equation true. For each value of one variable, the value of the other variable is determined. The fact that the solutions of linear equations are part of an infinite set of ordered pairs led to the idea that those pairs could be treated as points on a graph, and that those points would then form a line. This reasoning is why these types of equations are called linear equations. They literally form a line. And the idea of merging algebra and geometry then led to analytic geometry in the mid-1600s. Analytic geometry is a powerful combination of algebra and geometry. It was independently developed and published in France during 1637 by René Descartes and Pierre de Fermat. The Cartesian Plane is named for Descartes. So what is the Cartesian plane, or why do we have it, or how do we graph equations or linear equations? Well, it all started with the idea of how would you describe to someone the location of these 5 points so that they could draw them on another piece of paper without seeing your drawing? That's the question, and that's what these mathematicians were studying, and that's what they were trying to answer. Discuss with a partner. How would you tell your partner how to draw these 1, 2, 3, 4, 5 points without them looking at the piece of paper? Well, maybe you would tell them to start at one of the other points. Maybe you would use directional words like left or right, up or down, maybe north, south, either east or west, but it wouldn't be an exact replica without having more tools or more help. Now, adding this Cartesian coordinate plane makes the previous task simple, since the location of each point can now be given by just 2 numbers. They can all be represented by an x and y coordinate written as an ordered pair in parentheses x, y. With the Cartesian plane providing a graphical description of locations on the plane, solutions of equations, noted in ordered pairs, can be analyzed using algebra. The Cartesian plane is formed by the intersection of the x-axis and the y-axis, which are perpendicular to each other. It's also sometimes called the coordinate plane or the xy plane, but it's also the Cartesian plane. Now, the x-axis is horizontal, side to side, left and right motion, and the y-axis is vertical, which is an up and down motion. The axes intersect at the origin, which has the coordinate of 0, 0. That's where x equals 0 and y equals 0. And they form the 4 quadrants, often labeled with numerals 1, 2, 3, and 4. An ordered pair represents a solution to a linear equation and a point on the plane. The numbers represent the x and y coordinates, where you see in parentheses x, y. So x always comes first and then followed by y. And it matches alphabetical order, so it's very easy to remember. So here we have the point 4, 8 is shown on the Cartesian plane. That means you're moving 4 on the x-axis and 8 up on the y-axis. A linear equation has an infinite set of solutions. Graphing the pairs of x and y values which satisfy a linear equation forms a line, hence again the name linear equation. Always remember, linear means it's forming a line. One way to graph the line that represents the solutions to a linear equation is to use a table to find a few sets of solutions. And since a line is uniquely defined by any 2 points, finding 3 or more points provides the line and a check to make sure the points are correct. So let's graph the line y equals 2x plus 3. We'll make a table, pick some x values, and then calculate the matching y values to create ordered pairs to graph. Now we can pick any x values, but we will choose them so that the resulting points are, one, easy to plot, right? If you look at our coordinate plane, we really only have, from -5 to 5 on the x-axis nicely marked, and from -5 to 10 on the y-axis easily marked. And then we also want points, though, that are far enough apart to allow us to draw an accurate line. So for y equals 2x plus 3, here is our table. So while we only need 2 points to determine the line, it's good to check with some extra points. So we're picking 1, 2, 3, 4, 5 x values to find the y values, and then we'll have 5 points on the line. So we have x values of 1, 2, 3, and then we played around a little bit with 0, and then a negative x value of -3. So let's use the equation to fill in the y values in the table. For example, if x equals 1, we can substitute that into the equation, and that would give us a y value of 2 times 1 plus 3. If x equals 2, the y value would be 2 times 2 plus 3. If x equals 3, the y value would be 2 times 3 plus 3. We would have, for 0, 2 times 0 plus 3. For -3, 2 times -3 plus 3. We're inputting each x value into the equation so we can see the y value. And so we end up with a completed table with ordered pairs of 1, 5, 2, 7, 3, 9, 0, 3, and -3, -3. So these are just a few points on the line. These are 5. But there are an infinite number of ordered pairs that satisfy this equation, so we're going to draw a line through these points that represents the infinite set of solutions to this equation. And we can do that by just using a straight line and connecting the 5 ordered pairs. So this is what our line looks like. This is the line that is representing the solutions to the equation y equals 2x plus 3. The arrows on both ends of the line indicate that it continues forever in both directions. So those are important as well. It's not a line segment. It doesn't end there. You have to show your arrowheads to show it continues on and on. And because it is a line, it includes an infinite number of points representing all the real numbers that are possible for the line. Let's graph another line. Here we have the equation y equals -x plus 6. So we're going to use the table method and fill in the y values given the chart with the x values. We have x values of -3, -1, 0, 2, and 6. So we're going to start by using the equation to find the y values so that we can plot our ordered pairs and connect them with a line. So the y value for when x equals -3 will come from -3 plus 6. It's substituting in that x value into the equation. The y value for -1 will come from -1 plus 6. From x equals 0 will come from -0 plus 6. From 2 will come from -2 plus 6. And from 6, x equals 6, the y value will be -6 plus 6. Simplifying those expressions in our y column, we're going to get ordered pairs of -3, 9, -1, 7, 0, 6, 2, 4, and 6, 0. So now those are ordered pairs we can plot on the graph on the coordinate plane. So we have -3, 9, -1, 7, 0, 6, 2, 4, and 6, 0 on our coordinate plane. And now we can connect those points with a line to show all of the other points or all of the other solutions that are represented on this line, now continuing forever and ever in both directions. And that is, again, representing the solutions to this equation, y equals negative x plus 6. Let's do one more example. We're asked to graph the line using a table, the line being the solutions to the equation y equals negative 1/3 x plus 9. So if we substitute in our x values that are given to us in the table, we have x equals negative 3. So that would be a y value of negative 1/3 times negative 3 plus 9. We would have for x equals negative 1, negative 1/3 times negative 1 plus 9. For 0, we would have negative 1/3 times 0 plus 9. For 2, we would have negative 1/3 times 2 plus 9. And for x equals 6, we would have negative 1/3 times 6 plus 9. So the first thing we need to do is simplify those y values to get our ordered pairs. But something interesting that should happen when you simplify some of these y values is we get repeating decimals. We get, for the x value of negative 1, we get 9.3 repeating, and for the x value of 2, we get 8.3 repeating. So notice, when the coefficient of your x term is a fraction, we had negative 1/3, it's helpful to select points that are multiples of the denominator. If our denominator of 3 is going to affect the y values, it was good to, in this example, pick x values of negative 3, 0, and 6, because then the y values are integers that we can easily plot. We have negative 3, 10, 0, 9, and 6, 7. It's very hard, or it's impossible to know where on the graph negative 1, 9.33333 is. We would have to approximate where that y value is. And when graphing lines, we want to be very specific, very accurate. So we want to make sure when graphing we have those nice integer points. So that's why on this line, I'm only able to note those 3 points of negative 3, 10, 0, 9, and 6, 7, because I only know for 100% sure where those are on the Cartesian plane. So just be careful with some examples that are involving fractions. We do have to take care with what x values we're picking so we can get the most accurate line to represent all our solutions to our equation.